Yeah, thank you. All right, welcome to part 2. Right, so yeah, so so we have seen a proof of Balazs's theorem, right, which is from 1981. So in the Lucchesi-Murty book, they mentioned that, so they were not aware of this at the time when they published their 2004 paper, and they mention also in the paper that the fact that this is true for bricks was communicated to them in 2003 by 4 authors, Di Pina, Fernandez, Reed and Wakabayashi. So they had given another proof of it, but in the book they skipped that proof because they said that this is a much simpler proof. And it actually is more general, it handles all matching covered graphs at the same time, so you don't need bricks and all that. That being said, the next result that we will prove is actually for bricks, and the corollary of this for all matching covered graphs is corollary 7.6, I think, and that is on your assignment. Right? And so what we will prove is that for bricks, the following 3 are equivalent. This is my version of theorem 7.5. The actual version only says 1 and 2 are equivalent. It does not talk about 3 in the same statement, right? But the equivalence of 2 and 3 is clear because of Balazs's result, right? And in fact, 2 and 3 are equivalent for all matching covered graphs, therefore for bricks, okay? But we will prove that in the case of bricks, being solid is the same as being Birkhoff von Neumann. And I have written the definitions that I am using today in brackets. Right? So solid means that it is free of non-trivial separating cuts, and Birkhoff von Neumann means that the perfect matching polytope is exactly the fractional perfect matching polytope. Right? So we'll prove both implications, and of course in the grand scheme of things one can probably simplify, because we just need to prove a cyclic permutation. 1 implies 2, 2 implies 3, 3 implies 1, but I'm not doing that optimization. I'm just going to prove maybe 4 implications. But anyways, partly because the proofs are nice, we might as well just go through them. So given the time we have left, we will only do 1 implication out of these 2 today. We will prove that if there is a non-trivial separating cut, then there is a point in the fractional perfect matching polytope that is not in the perfect matching polytope. Which implication is that? What I said? 2 implies 1. Is it 2 implies 1? Okay. 2 implies 1. The contrapositive would say that if G is not solid, then G is not Birkhoff von Neumann. So, suppose that G is not solid, which by definition implies that G has a non-trivial separating cut. We have a brick and it has a non-trivial separating cut. Yeah? Say C. Our goal is to show that the perfect matching polytope is a proper subset of the fractional perfect matching polytope. In other words, we want to show the existence, maybe if you want to actually construct it, a non-negative 1 regular vector that does not satisfy some Edmonds constraint. And here by 1 regular, I mean for every tight cut the sum is equal to 1, but it doesn't really matter because it's a brick, so the only tight cuts are the trivial cuts, right? So 1 regular just becomes the degree constraints, right? So show existence of or explicitly construct a non-negative one regular vector that violates some Edmonds constraint. Yeah? Is that fine? Okay, as I present this, I realize that we will do something more general. Okay, but is the idea clear? So we'll actually do this for all matching code graphs. Okay, let me state basically whatever is necessary for matching code graphs. So we'll take a matching code graph that has a separating cut that is not tight. Yeah, of course in a brick it will not be tight. So we'll take a matching code graph with a separating cut that is not tight, and we will show this is true even for matching code graphs. Yeah, so in fact this is the more general thing we'll do. So now forget brick, let G be a matching covered graph, C be a separating cut that is not tight, and now our goal is the same. And here again one regular means now we can actually have non-trivial tight cuts in this graph. So by one regular I mean that on every tight cut the sum should be still equal to 1. Okay, that won't be too difficult. Okay, so we will construct in this case more general a non-negative one regular vector that violates some Edmonds constraints. And this would imply, if we do this, then in the more general setting this would imply that because it will be non-negative one regular, it will also satisfy the tight cut perfect matching polytope. Okay, so this will actually implies that the tight cut perfect matching polytope is a proper subset. Wait a second. Yeah, because it will be non-negative and one regular, it will satisfy all the tight cut perfect matching polytope constraints. Yeah, but it will violate some Edmonds constraints. So it will imply that the tight cut perfect matching polytope for this setting is a proper subset of the fractional perfect matching polytope. Yeah, and in the case of bricks, which of them are equal? Let's just remind ourselves. In the case of bricks, which two polytopes are clearly equal? Between the three, perfect matching polytope, tight cut perfect matching polytope, and fractional. Which ones are equal? Tight cut and fractional. Yeah? No.
Not what is happening.
This is what will happen in this case. We will still construct a one regular vector.
Oh, yeah.
Right? In the case of bricks, which ones are equal? Tight cut and fractional? Think again, think about the three polytopes. In the case of bricks, if I give you a brick, which one of these holds inequality? Really? This is in the tight cut perfect matching polytope, right? For every tight cut, x is equal to 1.
Also in the fraction.
But this is also in the fractional one.
Actually, fractional has a condition for this cuts.
For every odd set, I need at least 1.
No, fractional.
Ah, I am the one. Yeah, okay, yeah, you're right. Okay, yeah, I mixed up. Yeah, for some reason in the fractional case, I was putting the Edmonds constraints. Yeah, okay, good. Yeah, yeah. In fact, you're right. Yeah. Okay, good. So yeah, of course, yeah. So in the case of bricks, yeah. Yeah, what I was thinking was different from what I was saying. So yeah, in fact, the tight cut perfect matching polytope is equal to the fractional perfect matching polytope. Is that what I said? Yeah, because this has only non-negative and one regularity. This has non-negative and one regularity, but because there are no non-trivial tight cuts, they become the same. Yeah. Okay. Yeah. But it's a more general thing we are trying to prove clear, right? So we will assume that we have a matching covered graph that has a separating cut that is not tight. Clearly, separating cut that is not tight has to be non-trivial separating cuts. Every trivial cut is tight, right? And in this setting, we will show the existence of a non-negative one regular vector that violates some Edmonds constraint. Which Edmonds constraint do you think it will violate? Which one? For is there a specific one you want to violate?
Maybe this is C.
The separating cut itself, right? We will violate this separating cut's odd cut constraint. Okay, so in fact what we will do is actually the following. So the exact thing we will do here, construct a non-negative one regular vector x such that x of c is strictly less than 1. Yeah? Is the idea clear? This is the plan. We will give an explicit construction of a vector that does the job. Alright. The facts that we will use about C are exactly what is given. Separating cut that is not tight. The fact that it is not tight means that there is a perfect matching that meets the cut in more than one edge. Therefore, at least 3 edges. We don't even need at least 3, we need only greater than 1, but anyways, I'll write it. So, since it is not tight, there exists a perfect matching M0 such that M0 intersection C is at least 3. Since it is a separating cut, for every edge there is a perfect matching that contains that edge and meets the cut in exactly one edge. For every edge of the graph G, there exists a perfect matching ME such that E belongs to ME and ME intersection C is exactly 1. Yeah? I have basically given you all the ingredients. Now you need to come up with a vector that does the job. And I don't expect you to finish it today. So we can leave it as a DIY, right? So your goal is to use these perfect matchings, use this perfect matching, come up with a vector that is non-negative and one regular, but for this particular cut C, x of C should be less than 1. And the only perfect matchings you need to use in your convex combination are these perfect matchings. Right, so that's your DIY. Until next lecture. Use all MEs and M0 to construct all MEs. For every edge there is an ME. Well, it actually makes things very easy. The thing is you don't, okay, well, I'll just, yeah. You can try using fewer MEs, but I think that will be more complicated than using all MEs. There may be ways to do it with fewer MEs, I'm not sure. But yeah, actually all makes life a bit easier. The reason it makes it easier is, okay fine, I'll think just leave it, yeah. Okay, think about it, right? Okay, so that's all for today, that's the plan. And try to go over the general definitions and all anyways, right? Because there is a lot of stuff. You can see I also keep getting confused between all the things. Okay, yes, question? Yes, go ahead.
So, there, we wrote this, showing this goal implies the type-cut perfect matching polytope is a strict, strict subset of the fractional.
Yeah.
In case of bricks, they are equal.
Yeah, that's something that I was also confused about. Yes, I am also a bit confused by this because if I am proving this,
I think it for bricks, whatever you wrote there, for matching curve graphs that are not bricks, maybe this still holds. But for only for bricks, Edmonds polytope is a strict subset of type-cut perfect matching polytope, which is equal to
yes, if I just apply this plan to a brick, I have a separating cut that is of course not going to be tight, it's a brick, and I construct a non-negative one regular vector. So because it is a non-negative one regular vector, it will belong to the perfect matching polytope. No, it will
both tight-cut and fractional perfect matching polytopes.
Yes, it will belong to both the fractional perfect matching polytope as well as the tight-cut perfect matching polytope.
But not to perfect matching polytope.
But it won't belong to the perfect matching polytope because of this. Yeah. So in that case, we will basically conclude that the perfect matching polytope is the proper subset of the tight cut perfect matching polytope.
But if it's not a brick, this happens.
Yeah, if it is not a brick, then we will actually get a more general conclusion. I also got confused yesterday, so let me just think about it again. But yeah, I am also a bit confused. Anyways, as far as the proof is concerned, maybe you can forget bricks and just focus on this. And I will also kind of go through this again and see where exactly I am tying myself in knots, because I think I am also still tied in knots. I tried to resolve it yesterday, last night. I thought I did it before going for my swim, and now I feel that I am I've again tied myself in knots somehow. Okay. Yeah. Okay. Any other questions, concerns? Yeah, but it's the general plan here. So we have a matching chord graph, and you can forget about bricks, and we'll try to relate the two later.
Oh, I
Yes.
think both containments are strict for graphs that matching chord graphs that are not bricks, because we have this conclusion, and let's say you take some brick of the matching chord graph and get that vector, you can expand it and C will still be a separating cut that is not tight in the big graph, and you get strict containment everywhere.
So you are saying a matching chord graph which has two or more bricks. Because for bipartite graphs, everything holds with equality.
No, at least one brick.
Okay, you still have only one brick.
Yeah.
If the brick itself is not solid,
Yeah.
then the whole graph is not solid.
Yeah.
And then in that case, the perfect matching polytope is a proper subset of the tight cut perfect matching polytope.
Yeah.
And you are saying that the tight cut perfect matching polytope will also be a proper subset of the fractional perfect matching polytope. I think that is probably true, but I'll have to think through it again. Yeah. Okay, good. Alright, anyways, I'm quite confused right now, so any other questions or concerns? Okay, if not, we can stop recording and let's resume next time. Yeah, thank you.